All right, so linear regression. We're going to continue on with linear regression. Last time we talked about an introduction to linear regression. We talked about the different parts and stuff like this. We talked about it as simple linear regression, which is just two-dimensional. But I'm going to tell you a secret. Multiple linear regression is really not that different from just regular linear regression. The difference is that basically we are considering multiple features, right, to make one target. And remember, features are the things that we're using to make a prediction for. Target is the actual prediction that we want to match up with. So I think I gave the example of like height versus weight. So I think it was something like, I think I did height, or I think weight was like on the y-axis and height was on the x-axis. So the taller you were, the more likely our model would predict. Our model would predict like, oh, you are, heavier, right? So you can imagine that's like a linear relationship, but maybe there's some fluctuations from that point, right? Maybe, for example, some people who are taller are actually very light, or some people who are shorter are actually heavier than expected in the model. And so if we knew other information, for example, maybe we knew like if you, I don't know, you exercise a lot or something, or you eat vegetables, or something like that. Maybe there's a correlation between those parts, or maybe some factor of your genetics, right? Like maybe certain people with certain genetics will just happen to be, taller and stuff like this. If we knew those other features, we might get a better job on prediction. And that's what multiple linear regression is basically going towards. Is like we can use multiple features to make a prediction. So let's go pull this up. Okay, I was scared it wasn't loading. All right, so multiple linear regression. So I'm gonna, let's hear, spend a lot of time on those questions. Hopefully that's good. All right, so we're gonna kind of introduce this a little bit. I'm gonna just kind of show you guys a little bit of code here. So the main thing is that we're just, again, using multiple variables, features to predict one target. So I believe I took this from the curriculum itself. I'm just using the NP seed right here. 1, 2, 3, 4, a good classic. And we're doing a uniform distribution. These are just to generate data. So note this is going to be 18 to 65. We're grabbing 100 data points. And then this will also have an income right here with the standard deviation 0.5 and basically a normal distribution surrounded by, it's going to just be divided by this part. So it's going to use this array as basically its input in here. So in the end, and then note that we're just reshaping it so it's easier for us to see. And we're just going to plot it out so we can see it better. So if I, for example, just real quick, income, you could see those are the different values, right? And then if we looked at like 7, I don't even remember what these represented necessarily, but you can see here, because we reshaped it, each point now is its own separate thing. And it makes it easier for us to plot. Okay, so then we can see here is our linear regression line with our data points. So seniority, oh, that's what it was, and monthly income. Okay, so the idea here is that, and the idea is that we have these data points. If we didn't have, if we had just this guy right here, right, we would say, okay, like, can we predict monthly income from seniority? And that's what this black line represents. And so this again is our regression line. And so if you remember, basically this equation could actually be an equation line, right? Target is equal to the slope times the feature plus the intercept, right? Sorry, there we go. But what happens if we have multiple features, right? So not just seniority, but some other factors, right? Well, we can basically write it as saying, okay, well, there is some intercept to begin with, some slope times the feature, so a coefficient times, some feature, took a screenshot by accident. And we could do that for multiple features. So typically you'll see people write this out as different variables like W0, here's how I wrote it. The reason why I put W is because later on we'll use it as talk about like weights and stuff like this. We can imagine like different coefficients, right? Plus another coefficient times a new feature, plus another coefficient times a new feature. And you can almost imagine this as being something like a seniority being like number of years, is that for every, let's say if this model has a coefficient for this W1, let's say it's just W1 and X1 is a seniority, is that for every year you have in seniority, every additional year you have in seniority, you go up in monthly income by like, let's say like 20 or something, or like, I don't know, $20 or something like that. And so that would be a coefficient of 20. Basically saying, oh, for every 1 year of seniority, you have 1 unit of seniority, you go up by $20 or 20 units in the target. And that's essentially how you'd interpret this guy. And so if we had other features, like say W2 and X2, let's say X2 was going to be another feature we could have in value, your age. So maybe there's seniority in age. Maybe let's pretend we're independent from each other. But maybe, for example, just people who are older just tend to make more money. You would have something where it's like, okay, for every additional year older you are, you make an extra $50 per month. And so this coefficient then would be 50 for that feature. Of course, that's a bad example because those things are obviously correlated together and that causes a whole bunch of issues. But you can imagine multiple features that would have some kind of similar, as you increase in one value, it increases the other one, or even decreases. Okay, everyone follow me for that guy? Yeah, all right. So if we have multiple dimensions like this, if we have 2 dimensions, right, which is basically your feature and your target, that's a 2-dimensional plot. If we have multiple dimensions, let's say 3 dimensions, right? So we have a feature, and a target, we would expect our, instead of a line, basically would be some kind of like 3-dimensional plane. And so you can kind of imagine is that this, usually the z-axis, the y-axis is what we talk about as being like our target, right? And this is why we start using, like this w, like x1, x2, because it's a little bit easier for us to talk about when you talk about like does anyone know what the convention is for 50 dimensions? No, because there's no convention. It's just x sub 50. So the idea here, though, is that this plane is basically the best thing to fit across all these data points. So if this plane is very, very good at fitting these data points, you would actually expect the data points to be very close, if not on the exact plane. And what's kind of cool is if you imagine this now, like, I don't know if you guys ever dealt with like multiple dimensional, like, especially like multivariable calculus does a lot of this. But if you imagine like a projection, if I were to kind of like look at it sideways. So I usually use my hands for this part. So I'm gonna grab just like a random book that I have. So you imagine this is my plane that's on 3 dimensions, right? And so you can imagine like this is like the x, and then this is the target here. So this is x1 and y right here. And then let's say I have a new dimension like this. So y doesn't change, but now there's an x this direction. You can kind of imagine like taking a snapshot like this, like, oh, like there's our line right here. Or if I tilt this in a certain way, like you can kind of imagine like, oh, that's our line if we split it up in a different way. So you can kind of imagine is that when we do multiple linear regression, it's a bunch of little linear regressions put together. So you can kind of imagine like a slice of just those 2 dimensions, your target in one feature. The thing is that multiple linear regression is going to consider all of those features at once to make one multi-dimensional plane. And then we can kind of, so what's kind of interesting is that you might have a 2-dimensional plane like this, or sorry, a 2-dimensional simple linear regression that will perform better at first than if you looked at the same feature on multiple, because maybe there's other features that better explain this value here. And that's talking about like multicollinearity and stuff like that. Okay. Is this concept kind of, how do we feel about this concept of going from single or simple linear regression to multiple linear regression? Pretty good. Cool. You guys.
Yeah, and in that and in your equation, your line equation, there's actually an x0 there too, right? But x0 is always equal to 0.
There is an x. Well, yeah, there's an x0. It's not equal to 0. It's equal to 1. So you can imagine.
I'm sorry. Yeah, equal to 1. Correct.
Otherwise, but you had it right.
0. Yeah.
So it'd be like this. Yeah, and this is sometimes called, depending, like we'll talk about this as the bias. So this is kind of like your intercept. And so we can kind of think about like, oh, your x0 is kind of essentially your default value. And that's kind of a great way to interpret it as well. Okay, cool. Yeah, any questions or any follow-up on this guy? Okay, so one thing I'm gonna kind of point out this before you get into categorical is like, how do you interpret this? Like, let's just pretend you get your equations, right? And like, how do you interpret this? So I'm just going to write on here because I can write a little bit easier than I can type directly on here without making it too messy. So if I imagine if I have like, let's say like y, so y hat is our prediction, right? Is equal to, I'm just going to say like, let's say 30 plus, we'll say x1 is our seniority again, right? So let's say this is like 10 times x1 plus, I want to say 20 times x2. What's another good feature that we could use that's a continuous variable for income, monthly income that's related to some attribute of someone?
Education?
education, yeah. Let's say years of education. That's we can force into a continuous variable. Let's say years of education, right? So x2 is years of education. X1 is just like how many years you've been at the company. Okay. And so the way you would interpret this is like, okay, if you have 0 years of seniority, right? So you've never been at this company and you had 0 years of education, let's say past like high school, just to make it reasonable, right? So like, let's say you have 0 years of like you graduated high school and you started this job right then, you're expected, like based on this model, this might not be realistic, but your expected monthly income would be $30. Okay, and that's what that intercept is representing, right? Obviously, this model is not, I just pulled this out like in my head, right? But that would be what the model is saying, right? So what you can say this part is, okay, like how do we interpret this guy right here? So remember, X1 is the years of like at this company, right? Anyone want to try to, how would you interpret this 10 into something meaningful to your non-technical stakeholders?
For every 1, it goes up on a slope of 10.
Like every one, could you
year?
Give me, yeah, 1 year. Sorry, go ahead. I kind of interrupted you. You had it, Stephen. Yeah, so every 1 additional year of being at the company, you expect to make 10 additional dollars per month, right? Again, not a realistic, scenario, but like we're just gonna use these nice numbers. And so then you can kind of see,
might make more sense.
Yeah, if I had these values, probably what I should do is like add extra zeros to this, like, oh, like 300 or 3,000 or something like that. But again, we'll just pretend like you guys, this is like back in the 20s or something like that, where people made like $30 every month or something. So anyway, so that would be like, oh, every additional year, right? And then for this guy right here, let's say X2 is number of, what did we say X2 was? How many years you had past, high school, right? And so if you graduated high school and started this job, right? Basically, this would be 0, right? But if you had 1 additional year past high school, right, we expect you to make $20 more per month, at least based on this model. Let me ask you guys, how would you say, like, based on this model, at least in the way we defined it, what would you expect this X2 value to be if you didn't pass high school? Maybe you left a year early. What would this X2 value be, you think?
Would it be negative?
It would be negative, right? -1, right? If you it would be negative if you didn't, like if you left early, and then if you left a year early, -1, right? So this is kind of the way you can kind of interpret, your model. And what's nice about linear regression versus a lot of machine learning algorithms that we're going to talk about is that its interpretability is really straightforward. Basically, you can see exactly, you can say for X, for this amount of thing, you expect this increase. So for stakeholders, it's really nice because you can say, for example, if you hire someone who is 5 years in seniority, or let's say 5 years out of high school or something like that, so they had 5 additional years of education, you should expect to pay an extra $100 for them. And you can make those kind of predictions a lot easier. So that's kind of the way we interpret this. Okay, that makes sense to people? Cool, all right. So when I start using those equation stuff, you'll hear me kind of phrase it in those ways too.